In the previous video, we went through this development from this first version of the statement to another version, and then finally to this last version here, which I'll prove now. Okay, now before I actually prove this, let me go through some common mistakes. So what I'm going to do right now is I'm going to write out some incorrect proofs, and I'll talk about why they're incorrect. All right, so remember what we're trying to do. We're trying to prove a statement of the form P implies Q. All right, and so what we're going to do is we're going to assume P. We'll assume P. We put this in red here. X is even and Y is even. That's our P. And we're going to show Q. Essentially, we're saying we're going to assume P is true, and we're going to show Q is true. That'll tell us that this never happened, right? Because this is true, then false. And because that never happened, we know immediately that the final value is true, true, or true, otherwise known as true. Now, a common mistake is to assume Q and show P. So let me show you that common mistake right now. Now, this doesn't work, right? Because if you think of looking at this truth table here, truth table definition of P implies Q, it doesn't make sense to assume assume Q is true and prove P is true. Right, because our assumption is that P is true. Remember, why can we assume this? We can assume this because P is either true or false. If P is false, then we find ourselves down here, and it's always true. So we may as well assume P is true. All right, well, let me show you the mistake. And a proof that's not really a proof, we don't call it a proof. What we call it is a poof, because there's magic involved when you don't actually prove something. When it's a poof, it just poofs out of thin air. All right, so here's the poof. Here we will assume the conclusion. Assume x plus y is odd. So x plus y equals 2k plus 1 for some integer k. So x equals 2k and y equals 1. So x is even and y is odd. This is a completely incorrect proof. This doesn't prove anything because we assumed what we wanted to show. If you assume what you want to show, then you've proved nothing, right? We assumed the conclusion. All right, so this doesn't work. This is not a proof. This is a poof. Another incorrect proof, another poof, is that you might give a few examples, just a few examples. Let's see. Well, And when I used to have students in Math 189 actually do proofs, I would get proofs like this. Assume x equals, let's say 2. And y equals, let's see what's an odd, 3. So x plus y equals 2 plus 3, which equals 5, which is odd. End proof. Now this is not a proof either. This is just, remember, a proof is basically a recipe. A proof is a recipe that you could put any x and y in here that satisfy these assumptions. And then you would be able to show that x plus y is odd. Now this is not any x and y. This is a specific x and y. So this is not general enough. This is a specific example, not enough. Even a finite list of 100 examples is not enough because it doesn't cover all possibilities. We want all the possibilities. Okay, how about another one? Let's see, let me do another not general enough. Poof. So assume x is even. Okay, so let's say assume x is even and y is odd. So x equals 2k and y equals 2k plus 1 for some integer k. So x plus y equals 2k plus 2k plus 1, which equals 4k plus 1, which is equal to 2 times 2k plus 1. Oops. 2 times 2k plus 1. Maybe the proof writer even says something like, since k is integer, so is 2k. So x plus y is odd. Now it looks correct, but the only problem is that we assumed that x was 2k and y was 2k plus 1. It's general, but it's not general enough. Because we can't assume, like let's say that k was 1, right? Then x would be 2 and y would be 3. But that doesn't take into account the case when x is 2 and y is 5. That doesn't take into account the case when x is 4 and y is 101. Right? It's not general enough. So to fix this, what we need to do is say, use a different letter. Okay, so x equals 2k and y equals 2, let's say m, 2m plus 1 for integers k, m. Now this does take into account all possibilities. I mean, it could be that k and m are the same number. If k and m are the same number, then we take into account let's say both k and m are equal to 1. Then we have x is 2 and y is 3. But we take into account all possibilities, because it could be that k is 1 and m is 2, and then x would be 2 and y would be 5. It takes into account all possibilities. So is k plus m. Okay, and so this here is a valid proof. It's not a poof, it's a proof. Here we've stated our assumptions. And notice that this next line follows directly from the one that came before, right? So assume x is even and y is odd. So if x is even, then the definition tells us that x equals 2k, where k is an integer. And y, if y is odd, then the definition tells us that y equals 2m plus 1, where m is an integer. Right? This follows directly from the fact. So we state our assumption, and then the way evens and odds look follow directly from that fact. Then next, now we have a handle on what x and y look like. X is 2k, y is 2m plus 1. So it follows that x plus y looks like this, which can be turned into this. Now we say, finally, where everything lives, k and m are integers, so k plus m is an integer. And then we finish with our conclusion. This is a proof.